For today's lesson, we are going to finish our coverage of equivalence relations, so section 4.5, and then we are going to move towards section 6.4 and discuss strong induction and the Will ordering principle. Now, at the end of our last lesson, I posed the following question. Can we go the other way in the direction of theorem 4.5.4, which told us that if we had an equivalence relation R, then A mod R is a partition of A. So would we be able to, if we are given a partition F on a set A, can we come up with an equivalence relation R so that A mod R is equal to the given partition F? And the answer is yes. And so that's what we are going to prove. And I'm going to do things slightly different from the book. The book breaks the result between page 221 and page 223 into a theorem that is followed by two lemmas upon which it relies. And so what I am going to do is prove this directly, but the lemmas that the book separates are incorporated into my proof. So how are we going to find the equivalence relation? So to see that, let us revisit our slide on the definition of a partition. And what we have in our assumptions is that we have a family of sets such that the union of all the sets in the family is equal to the set A itself. The family of sets is pairwise disjoint, so in this family of sets, given any two distinct elements, so in other words, two distinct sets in the partition, call them X and Y, their intersection is empty. And of course, the empty set is not contained in the family of sets. And this is our key, because for an equivalence relation, we want to have reflexive, symmetric, and transitive. And so if we can define an equivalence relation where two elements in A will be related if and only if they are in that given set, in some set in the partition, then that will be enough because of the pairwise disjointness. So that's going to be our approach, and so let me go ahead and write that down. So we're going to go ahead and consider the relation R, which is going to be composed of those tuples A comma B in A squared, the Cartesian product of A with itself, such that there exists some family, in the family of sets, there is some set, actually let's go ahead and call this X. There exists some family X in the family, such that A comma B is an X. Now, note about the book. In the book, the same notation is used, just that instead of writing A comma B as an X, the ordered pair A comma B is in the Cartesian product of X with itself. And so X cross X. And so that's just a little side note in terms of the notation that is in the book. But now, if we were to have this relation R, we can then see if it's reflexive, symmetric, and transitive. And so for reflexive, we need to have that A comma A is in R for all A in for all elements in the set A. So let's go ahead and let's choose some element lowercase a in capital A. Then, since F is a partition, we will have that there exists some set X in the family such that A is an X. Therefore, A comma A is an X squared, which implies that A comma A is an R. Since we found that existence of X, and now we have that the ordered pair A comma A is in fact an R. And so that will take care of reflexive. For symmetric, now we want to suppose that A comma B is in R. Well, by definition of how we define our relation, that means that there is some X in the family such that A and B are in X. Therefore, B comma A is in the Cartesian product of X with itself, which implies B comma A is in the relation, so it is symmetric. And similarly, for transitive, we end up getting, now we want to take A comma B and B comma C to be in the relation. And so we want to show that then A comma C must be in the relation. Now, applying the definition tells us that there exists, because we have A comma B as an R, that means that there is some set in the family. So we have there exists X in F. But we also have B comma C is in R. So that means that there exists some other set. Let's go ahead and call it Y. And so we have such that A and B are both in X, and B comma C are both in Y. In particular, we are now in trouble because B is in the intersection of X and Y. Since F is a partition, we must have, by the definition of the pairwise disjoint, what we deduce is that since X intersect Y is non-empty, they must be in fact equal. And so we see that from the contrapositive of this statement. If the intersection of X and Y is non-empty, then X is equal to Y. So we have that X must be equal to Y, which shows that now A comma C is in X, which then tells us that A comma B is in the Cartesian product of X with itself, which in turn tells us that this is in R. And so we have, through our scratch work, that this here is the equivalence relation that we want. Because upon having it this way, we're going to have that this is going to be an equivalence relation. And now, when we look at A mod R, that is the collection of all the equivalence classes, the equivalence classes themselves are sets. And the way that everything is being constructed, because now we have shown that A mod R is a partition, we will have that is exactly the family of sets that we want. So we have A mod R. We want to show that this is equal to our partition F. Alright, so we're going to do a double set inclusion. So we want to show that A mod R is a subset of the family of sets, and we want to show that the family of sets is also a subset of A mod R. If we show both of those subsets containments, then we will have A mod R is in fact equal to F. So let's go ahead and get started. So let's go ahead, we know that in A mod R, all the elements are going to be equivalence classes. So if we choose, actually let me change this to lowercase a. So let's choose some equivalence class in A mod R. Well, if we choose an equivalence class, we know that A is going to be in the equivalence class. But now A is an element of A. So now if we put those together and the fact that F is a partition, we have that A is in the union of F, which is equal to A. But now, and so here we're using F as a partition. So we have A as an A, or capital A. Because this is a family of sets, we know that there must be some set capital X that contains A. So this implies that there exists some set X in the family of sets such that A is in capital X. So let's keep in mind what we are trying to do, because we're working with elements now, but we want to show an inclusion. So we chose this family of sets. We chose this equivalence class A in A mod R, and we want to show that this subset is inside the family of sets. And the way we are going to argue that is by showing that this equivalence class of A is in fact this set capital X. So claim, so suffice it to show for at least the one direction that we are working on now, that A is equal to X to show that A mod R is a subset of the family of sets. And so now we have another equality we want to show. So this is our second statement, and we're going to be proving this here, because if we prove this, we get this here. So let's do that. So let's go ahead and choose AB in the equivalence class of A. If we choose a B in the equivalence class of A, that tells us that A comma B are in the same equivalence class. And so we have A comma B are both going to be in R. But now if A comma B is in R, this is telling us by definition that there must be some other set in the family of sets, let's go ahead and call it Y, such that A and B are both in that set Y. So now there exists some set Y in the family of sets, such that A and B are both in capital Y. But now we have that A is in both Y and in X. And since now F is pairwise disjoint, we have that these two sets are equal. So since F is pairwise disjoint, consequently, we have now shown that that B is in X. And now this tells us that the equivalence class of A is a subset of capital X. So conversely, if B were an X, and so now we have shown this direction, now we want to choose a B and X and show that that B has to be in the equivalence class of A. So if B is an X, then A comma B is in R, since A is in X by assumption. So we started with our X containing A. So we have A is in X. We now have B is in X. So we satisfy this condition that there is some set in the family of sets such that those two elements in the ordered pair are both in the set. And so we have our A comma B is in R. And by definition, we now get that B is in the equivalence class of A, since this consists of all those elements C and A, such that A comma C is in the relation. So this gives us now the other containment. So X is a subset of the equivalence class of A. And so now we have shown that these are in fact equal. And so that will show one side, because now we have X is equal to the equivalence class of A, which in turn tells us that the equivalence class of A is an element of the family of sets F. So that shows that A mod R is contained in the family of sets. And so it remains to do the converse, but what I'm going to do next is I'm going to go ahead and formally write up the proof that we have done up to this point, fill in the details that I said verbally so that they are in front of us, and then finish it off with the remaining statement. So now that we have done the scratch work for most of the proof, here is the formal write-up for the theorem. So let me go ahead and zoom in. I'm going to just go through parts of this argument. It's exactly what we conveyed in the scratch work, but I do want you to have two different ways of approaching the theorem. They're both the same, but if you compare this formal write-up with the one in the book, there are differences. In the book, there are two lemmas that were done before proving the theorem. In the proof that I have here, those two lemmas are not present, but rather can be inferred through the argument that is given here. And so in the end, we do have that both statements are essentially the same, just that the proof in the book does extract those two lemmas. So be mindful of this when working through a long proof. Sometimes it is instructive to isolate a result that allows you to simplify your final proof of the theorem. And so go ahead, compare this write-up with the one that's in the book, see the pros and cons, and that gives you a strategy for attacking longer proofs in the future. So let's see. So if we were to approach the theorem directly, as we are doing, we first need to establish that we have an equivalence relation R, which we did in our scratch work. And so we can go ahead and we have our formal proof. So we have F as a partition on A, and we define the relation as we did. It's those ordered pairs A comma B in the Cartesian product of the set A with itself, such that there is some set X in the family of sets F, such that A comma B are in X. So we claim that R is an equivalence relation. We do the same thing that we did in our scratch work. We choose an A in A. We show that the identity relation I sub A is contained in R, because that's what we did. We show that A comma A is in R. So we do show that I sub A is a subset of R, and theorem 434 tells us that a relation is reflexive if and only if the identity relation, that is, the collection of all ordered pairs of the form A comma A for each A in the set A is a subset of R. And so we do have that R is reflexive, and that's where we are here. So then we show that it is symmetric. To show that it is symmetric, we choose an A comma B in the relation. By definition of the relation, that guarantees us that there is some set X in the family of sets, such that A and B are both in capital X. And now the definition tells us once more B comma A is in R, and it is symmetric as a consequence. For transitivity, just as with our scratch work, we choose our AB, B comma C in the relation R. Then by definition, now we have that there are two sets. They may not necessarily be equal, but we know that there are two sets X and Y in the family of sets with the property that that A comma B tells us A comma B are both in X, and the B comma C tells us that B comma C is in some set Y. Now we use the fact that F is pairwise disjoint. Since B is in the intersection and they're pairwise disjoint, they must be equal. And therefore, R is transitive, and that shows that it is an equivalence relation. So that shows the first part of the claim. And now the next part is to show that the family of sets is equal to A mod R, where that is the set of equivalence classes under the relation R. Well, we're going to show this by showing that the family of sets F is a subset of A mod R, and A mod R is a subset of the family of sets F. So to do that, we take an equivalence class A in A mod R for some A and A. Now, by definition of F being a partition, we know that the union of all the sets in the family of sets, that is equal to A. Since A is an A, we know that there is at least one X in the family of sets. And actually exactly one X since F is a partition, such that A is an X. So we claim that the equivalence class of A is equal to X. Because what we want to do is show that if the equivalence class of A is in A mod R, then that equivalence class is in F. And so if we show that they are equal, we are done. So we're going to claim that they're equal, and we're going to show this claim. So we're going to choose a B in the equivalence class of A. That tells us that, oh, 1 second, there's a typo here. Here it should be A comma B is in R. So remember that the equivalence class, by definition, let me just write that down since there was a typo and I want to emphasize. By definition of the equivalence class, this is the collection of all elements of A such that X comma A is in R. And since we have that R is an equivalence relation, we have already shown that up here, we can write this as A comma X or X comma A. And so we can change the order here since we know it's an equivalence relation. So we have A comma B is in R. And by definition of the relation R, we know that then there must be a subset Y in the family of sets such that A and B are both in that set Y. And that's another typo. Apologize for that. So we have A comma B is an X. Now, since A is in the intersection of Y with X, and F is pairwise disjoint, X is equal to Y, and therefore B is an X. And so we're just doing the scratch work that we just did, and now we have that the equivalence class of A is a subset of X. And now conversely, we have B is an X. We choose a B and X. We use the definition again of R to say that then A comma B is in R because again, by assumption, we have that A is in X. And so that's the crucial assumption we're using throughout this. A is in X. So we now have A comma B is in R. Therefore, B is in the equivalence class of A, which shows that X is a subset of the equivalence class of A since we chose an arbitrary B in X. And so now we have the equivalence class of A is equal to capital X, and that shows that A mod R is a subset of the family of sets. And so now we have to just show the remaining subset. And so let's go ahead and do that now. So conversely, let's go ahead and choose X is in the family of sets F. So then, we know that F is a partition. Since F is a partition, we know that the third property of a partition tells us that F does not contain the empty set. So we know that X is non-empty. So let us go and choose an A in X. And now we claim that the equivalence class of A is exactly equal to X because that will show us that then X, if it's equal to the equivalence class of A, the equivalence class of A is in A mod R. And so that will give us the other containment that we want to show. And so we claim this, but we just did this proof. We did it right here. We claim that the equivalence class of A is equal to X, and if we go through the same exact argument, we will get the proof. So proceeding, as in the previous claim, shows that the equivalence class of A is equal to X, and thus X which is then the equivalence class of A, is in A mod R, which concludes the proof, which allows us to conclude that A mod R is in fact equal to F, and that finishes the proof. Now, the reason I went about this proof differently than the text is to convey that the lemmas, the way that the book separates the proof, that way that it naturally happens is that we first try to prove the theorem, and then we realize, as we get to this step here, that we're proving the same thing again. So wouldn't it be worth to separate and isolate that statement and have it as a standalone result that we can then quote later? And that's exactly what the book does. But the thought process is not indicated. And so here we went through, we proved the statement, and we see that this statement here appeared in two aspects of our proof. So we can go ahead, copy this chunk of the proof, and try to create a new lemma that is standalone. And that's what the book does. So now we have lemma 458. Suppose A is a set and F is a partition of A. Let R be the equivalence relation determined by F. And so that's the way that we define R, our R. And suppose X is in the family of sets and lowercase x is in the set X, then the equivalence class of lowercase x is equal to the set X. Now, here we have the proof that we had for the claim. So I've copied it over. So the only difference is that instead of using lowercase x, it's now lowercase a. And we can run through the argument. We can choose a lowercase a in A mod R. And we can, so this part is not needed, but we claim that this part here, that's what we are trying to do here. And so the proof of the lemma is this portion right here. So let B be in the equivalence class of A. We run through the definition that shows us eventually that we do have that B is in X. And so we do have B is in X, and that tells us that the equivalence class of A is in X. Then we do the conversely part, we choose a B in X, we run through the argument, and we show that X is in fact in here. And so the portion of the proof that is relevant to the lemma is just this portion right here that is separated in blue. And that's the proof for the lemma. If you compare that with the text, that's exactly the same argument. And so just the takeaway from this is that there will be times when you will be working through a proof of a theorem that is rather involved, lengthy, and in your scratch work, you can go ahead and separate a certain statement, have it standalone, and now your theorem, your final proof, will be more streamlined in that you can refer to that lemma that you isolated. Put that at the before the theorem, refer to that lemma in the proof, and now your theorem is shorter. And so that's just the thought process for how one comes up with these lemmas. Usually what happens, as we see here, is one proves the theorem, then we see we can separate lemmas and then put them at the front. So next we are going to move towards section 6.4 of our text and discuss the principle of strong induction. Now, it's the only difference between this statement and the principle of mathematical induction is that the inductive step has changed. So let's go through the statement. I've written it in a general form. And so we're going to go ahead and suppose that n naught is some positive integer, but also n naught could be also 0. So I'm just going to go ahead over here. The positive integers is not necessary. We can say that it is true for the natural numbers. So we have some n naught, and suppose that we have statements p of n, where that is a statement for each number n that is greater than or equal to n naught. If we know that the base case is true, that is, p of n naught is true, and the inductive step that for every natural number k greater than or equal to n naught, if p of k is true for k less than n, then p of n is also true, then we can conclude that the statement P of n is true for every n greater than or equal to n naught. To see how this principle of strong induction is valuable in a way that the principle of mathematical induction fails us. So next we are going to see how the principle of strong induction allows us to prove the following theorem. Every integer n greater than 1 is either prime or a product of two or more primes. Up to this point in the course, we have only shown that if we have some integer n greater than 1, then if we have its smallest factor that is greater than 1, then it must be prime. So we have shown that, but we have not proven this theorem that every number is a product of primes, or it's a self-prime. And when I say every number, I mean every integer greater than 1. And this is still not the best possible result, because where we are building up towards is what is known as the fundamental theorem of arithmetic, that every integer greater than 1 can be written uniquely as a product of primes. And so this is the existence portion of that uniqueness theorem that we will be proving later. And so, how do we go about proving this? To use strong induction, well, we first need a statement. So let us go ahead and give the following statement. So for n greater than or equal to 2, and so specifically for n an integer with n greater than or equal to 2, let S of n be the statement n is prime or n is a product of primes. So that is our statement. Now, to apply this principle of strong induction, we need to show the base case and the inductive step. So for the base case, we have S of 2 is true since 2 is prime. So nothing to show. And so now for the inductive step, what we are going to do is assume that P of k is true for all k less than n. So now, let n be greater than or equal to 2, and suppose that S of k is true for all n, for all k less than n. And so now what we want to show is the consequent of the conditional. We want to show that P of n is also true. So we want to show that P of n is true. Well, to check if I wrote P of n, S of n. Well, there's two cases. Case 1, n is prime. Then S of n is true. And so in this case, there is nothing to show. Case 2, n is not prime. But if n is not prime, by definition it is composite. It's composite. And so there exists some integers a and b, and specifically positive integers, with a and b being both greater than 1, such that n is equal to a times b. And now it is at this moment that we get the value of having strong induction. Because if we were doing just regular induction, we would be focusing on n minus 1 and wanting to show that s of n is true. But the problem is, if we have some number, say n, takes 6. The prime factors of 6 are 2 and 3. When we look at the next number after 6, it's 7. 7 is prime. So the factors have nothing in common. With strong induction, we are able to then look at the following. So we have n is equal to a times b. But we also know that the factors of n, a and b, are both greater than 1. So then we have that n over a and b are both strictly less than n. By strong induction, which I'm going to abbreviate to, so by our inductive hypothesis, which I'm abbreviating to IH for the scratch work here. So by the induction hypothesis, we have that S of n over a and S of b are true. But that tells us that n over a is a product of primes. And similarly, that tells us that b is a product of primes, or is itself prime. And as a consequence, we end up getting n over a can be written as some product of primes, or is itself prime, and b. And then we can multiply both of those together, since n is equal to a times b, and we get n as a product of primes. And that's what we are going to be doing. So let's go ahead and formally write this up. So here is the formal write-up of the proof of Theorem 642 up to where we left off in our scratch work. So as before, we have n is greater than or equal to 2, so an integer. We have our statement S of n is prime, or n is a product of primes. Since we are going to be doing strong induction, we want to inform the reader, so we have this phrase here, we proceed by strong induction on n. Since 2 is prime, we have that the base case holds, so this tells us now that S of 2 is true. So now suppose that S of k is true for all k less than n. And so here it's implicitly understood that k is greater than or equal to 2, but strictly less than n. By the principle of strong induction, it suffices to show that S of n is true. If n is prime, then S of n is true, so nothing to show there. So suppose n is not prime, that is, n is composite, then we have factors a and b, integers, such that 1 is less than a comma b, less than n, and we have n is equal to a over b. But now, from the definition of it being composite, we have that because a and b are both greater than 1 and strictly less than n, our induction hypothesis tells us that S of a and S of b are true. And so it follows that S of a and S of b are true by our induction hypothesis. And thus, we have that a is equal to p1 times p2 all the way to some p sub t, and b is equal to q1 times q2 all the way to some q sub s, where each p sub j and q sub j is prime. Now something about the notation here. I'm writing p1 times p2 times p sub t, and this is telling us that a is prime or a product of primes, because if t could be equal to 1, and in that case, a would be prime. Similarly, with b, we have that this is equal to q1, q2, all the way to some q sub s, but s could potentially be 1, in which case b is prime. And so thus, n, which is equal to a times b, is equal to p1, p2, all the way to some p sub t times q1, q2 through q sub s, which shows that S of n is true. And now, at this point in an induction proof, we could finish the proof right here, because we have already said that it suffices to show that S of n is true. And so we could finish the proof over here and be done, or we could just add that extra sentence at the very end by the principle of strong induction, which I'm going to abbreviate to PSI. We conclude that S of n is true for all n greater than or equal to 2, which gives the theorem. And so we're done. We have now finished the proof of the fact that every integer greater than 1 is prime or is a product of primes. So the next result we are going to discuss is Theorem 644. And it's a very intuitive statement. Every non-empty set of natural numbers has a smallest element. Now, the book proves this using induction. A pet peeve of mine when it comes to the well-ordering principle is that at times it is taken to be a consequence of induction when actually more is true. It turns out that induction is equivalent. So when I say induction, what we are going to see in a moment is that mathematical induction, strong induction, and the well-ordering principle are all equivalent statements. And so I'm not going to prove this just yet. We are going to see how to use the well-ordering principle, and then we are going to conclude today's lesson with the result that tells us that all these statements are equivalent, but that will be proven at the start of the next video. So let's see how to use induction. Let us revisit the division theorem. So we've proven this using the principle of mathematical induction. A is a natural number, B is a positive integer, then there exist unique integers q and r such that A is equal to B times q plus r. And r satisfies the inequality 0 less than or equal to r, which is also less than b. Now, I'm going to go ahead and switch the natural numbers over here to a z, as the statement still holds in this case. And I'm going to prove the existence portion of this theorem using the well-ordering principle. And so let's go ahead and do this. So existence portion. So for the uniqueness, we will still need to do the proof that we did earlier. But the existence portion is satisfied if we can prove the existence portion using the well-ordering principle in a very nice way. And the first time you see a proof using the well-ordering principle, it can be very ad hoc in how these statements come about. And so I'll talk about what we are doing. So here's the idea. The well-ordering principle tells us that there is always a least element for any non-empty subset of natural numbers. And so what we want to show is the existence of the remainder. And so we want to show the existence of the remainder and then show that the smallest such remainder that is positive, or non-negative to be precise, satisfies this inequality. And so here's what we are going to do. We're going to construct a set that is a subset of the natural numbers with that in mind. And so the first thing we are going to do is the following. So let's go ahead and take a to be an integer. We're going to take b to be a positive integer. So let a be in z and b be a positive integer. And define, consider the set S. And this set depends on a and b, so I'm going to write the a and b as subscripts. And now what we are going to do is look at our equation here. We want to find a set in terms of the r, so this will be a minus b times q. But we don't know what q is, so we're just going to let q be arbitrary. It's going to be some arbitrary x. And so this is going to be the set of numbers of the form a minus b times x, such that x is an integer, and a minus b times x is greater than or equal to 0. And so just like that, we have our set. But now, by construction, we know that this here, a minus b times x, that's non-negative. So this is a subset of the natural numbers. Now, before we apply the ordering principle, we need to establish that this set is in fact non-empty. So let's do that. Well, x is any integer, and so we can go ahead and choose x to be 0. If we choose x to be 0, then we have that this is exactly a. And so that will give us one candidate. So now observe that a is an a comma b if a is greater than or equal to 0. And so here we have now taken x to be 0, and so we get back a, and so we do have that a is in this set. So what if a were negative? So if a were negative, we need to establish that there is a positive element in this set, or a non-negative element in this set. But the thing is, we just want to show it's non-empty, so we just need to show the existence of 1. That's all we need to do. So one option is to take a, but specifically a minus 2ab. So then a minus 2ab, and so here we have our a, we have our b, and so now we have chosen our x to be 2 times b. But this here is equal to a, and then 1 minus 2b. But now a is negative, and b, by assumption, is a positive integer, so now we have 2 times b being positive, but 1 minus 2 times b is going to always be negative. So we have negative times negative, so this is positive. And so we have that this here is positive, since a and 1 minus 2b are negative. Thus, a minus 2ab is in S of a comma b if a is negative, which shows that S of a comma b is non-empty. Now we can apply the ordering principle, which I'm going to abbreviate to WOP. By the ordering principle, there is a least element, which we're going to call R, of SA comma B. So now we want to show that R satisfies this inequality. And so again, we're proving only the existence portion, so we're not showing uniqueness. So we just want to show that this R satisfies the inequality that we want. So R, being an SA comma B, tells us that R is equal to A minus B times X for some integer X. And so I'm going to go ahead and call that X Q. So then, there is a Q and Z such that R is equal to A minus B times Q, and so in other words, A is equal to B times Q plus R. So we got that. And we want to show that this inequality holds. We know that R is non-negative, because that's what it means to be in here, so we know it's non-negative. So we know R is non-negative, and it suffices to show that R is strictly less than B. So now we're going to do a contradiction. So towards a contradiction, suppose that R is greater than or equal to B. Well, if that's the case, what if we subtract B from both sides of this equation? So then we now have R minus B is equal to A minus B times Q minus B. And so I'm going to go ahead and write this as A. So just write it all together. So minus B. But now that becomes A minus B. And so now we have a Q plus 1. So we got that here. But here is where we have to take into account what is the contradiction we want. We have A, we have B times Q plus 1. So we have something that's now in the set. And so this here is in here. So consequently the left-hand side, R minus B, is in that set. So therefore, R minus B is in S sub A comma B. R minus B is strictly less than R. And R minus B is strictly less than R. But this is a contradiction, because we said that R, by the ordering principle, was the least element. And that's what we had right here. So by the ordering principle, there is a least element R. We just exhibited a smaller quantity that is in that set. And that is our problem. Which contradicts that R is the least element of S sub A comma B. Consequently, it follows that 0 is less than or equal to R, which is less than B, which shows the existence portion. Portion of the proof, and we're done. And so that's one of the aspects of the ordering principle. We are able to do proofs such as these, but they rely on the clever choice of the set. As we see more proofs like this and in your future courses, we get an eye for how to construct these sets. And so the idea is you want to choose it in such a way that you can get the quantity that you want out. And so in our case, we are trying to show the existence of this R. And so we chose the set of all the possible R's by writing this set to have all the A minus BX's and building into it that this was always non-negative and therefore a subset. And so now we have another way of proving the division theorem, assuming the ordering principle. In our textbook, in this section, the division theorem is also done, and they do it using the principle of strong induction. So now that gives you 3 different arguments for doing the same exact theorem. Induction can also allow us to prove Binet's formula from 1843. And so what it states is that the m Fibonacci number can be written as follows. 1 plus root 5 over 2, all of that to the n, minus 1 minus root 5 quantity over 2 to the n, and everything over the radical of 5. Now let me just mention here quickly the Fibonacci numbers. So we have f0, we define it to be 1, f sub 1 defined to be 1, and then we can define for n greater than or equal to 2, f sub n to be f sub n minus 1 plus f sub n minus 2 for n greater than or equal to 2. And so what we get is that then f F2 is going to be 1 plus 1, 2. F3 is going to be 2 plus 1, 3. F4 would be 5, 2 plus 3. And then we get 8, 13, so on and so forth. So now, as a historical note, we do call them the Fibonacci numbers. But these numbers date much further. So they were first discovered by Indian mathematician and poet Pingala around 200 to 300 BCE. And they arise naturally in Sanskrit poetry. It should also worth noting that Pingala was the first one to discover the binomial theorem and the binomial coefficients by looking at its relationship with Sanskrit and poetry. And so that's the natural occurrence for these numbers. In the West, of course, we call them Fibonacci numbers, and then in the case of the binomial coefficients, we call them Pascal's triangle, but they have been known for over 2,000 years. So, in the book, this formula due to Binet is proven using induction, and I'm not a fan of that proof. The reason is that, yes, you can prove it using induction, but the thing about induction is that it works great when you know that there seems to be a pattern holding for every n, and it gives you the tools for proving said pattern. But it does not tell you why that pattern even exists. If we prove this using induction, as the book does, it doesn't indicate in any way or form where these quantities are coming from. So where do they arise? And the answer is eigenvalues and eigenvectors. If we instead view this through the lens of linear algebra, then we can prove this in an easier way while simultaneously uncovering where the radical 5 and the golden ratio, where they arise from. And so what I will be doing is posting a optional video that goes through the proof using linear algebra of Binet's formula. And then you can compare with the proof that is done in the text using induction. To finish it off for today, I'm going to discuss the various equivalences that we actually have for induction and the well-ordering principle. So we have covered the principle of mathematical induction. As I mentioned, we don't prove it in this course, but this can be proven from the Zermelo-Fraenkel axioms for set theory. In other texts, one usually proves that the principle of mathematical induction implies the principle of strong induction, and then induction implies the well-ordering principle. But what is actually true is that all of these statements are equivalent, and that is represented in this theorem. Principle of mathematical induction, principle of strong induction, and the well-ordering principle are all equivalent statements. And so what I will be doing at the start of our next lesson is going through the proof of this theorem, that each of these statements are equivalent. I will be skipping over some, and namely the ones that are already in the text in section 6.4, where well-ordering principle is shown to be implied from induction. And so we will see the other steps.